So, um, so as I mentioned in my announcement email, I've extended the deadline for homework 8 up until Monday for part 1, and then Wednesday for part 2. And of course, we'll have the quiz next week, for which actually on Wednesday and Friday I won't be here. So Dr. Liu will be doing a review session on Wednesday, and she'll be conducting the quiz on Friday. I'll post a sample quiz also by Monday, so you can take a look at that. I'm thinking maybe I'll post homework 9 also. That will be due April 9th, Saturday, right after the quiz. How's that work? You don't like it? Well, okay, then happy April Fool's Day to you. um, so, um, so yeah, other than that, I think there's what I plan to do today is to essentially finish out the handout from last lecture, and that will allow you to do problems 3 and 4 on homework 8. So very quickly, what we did last time was to try to come up with a way to deal with these inclined supports. So let me ask you this, I guess, before I begin. This is a roller inclined support. If I have a pin which is at an inclined support, how do I deal with that? Instead of the roller, if I have a pin that is at an incline, what changes would I need to make to the code to account for that? Nothing, right? A pin inclined is same as this pin. It just constrains displacements in x and y. So pin inclined doesn't mean really anything. It's the exact same thing as what I have a regular pin as a here. But the inclined support for the rollers definitely does require some changes. And I mentioned to you last time, the way that you would deal with that is at the end of the process, when you've already come up with the set of equilibrium equations for the truss. So you remember we kind of proceed for a problem that has inclined supports. We proceed with it exactly the same way that we would do as for a regular truss with no inclined supports. We construct the big stiffness matrix, as I showed to you, something like this, by assembly of all small element stiffness matrices. Some of the degrees of freedom would be free and the others would be specified just as before. The only trick here is that for supports that have an incline, we can't really say that the global 3 and 4 degrees of freedom, we cannot distinguish which one is fixed, which one is free, because it's a mix of those two. Essentially, it can move in the x double prime direction and it is fixed in the y double prime direction. So somehow I need to take those 2 degrees of freedom from the global coordinate system and leave the others alone, actually. So only those 2 degrees of freedom, I need to modify them to d3 double prime and d4 double prime. And the same thing for the forces also. So let's see how we did that last time. We said that in order to modify 3, 4 to 3 double prime, 4 double prime, we'll use the transformation matrix that we've been using for every other quantity. So transformation matrix transpose acting on the global degrees of freedom gives me the local or the inclined degrees of freedom, I should call it. So let's call this inclined degrees of freedom. And what we'll do is we'll take this system of equations, which I've written down here as k times d is equal to f. That was the original system we had. And what we'll do is we'll pre-multiply that D matrix with this T transpose. So if I do that, then if I take my system of equations and I insert a matrix that shouldn't really be there, then I've changed my system of equations, right? So instead of that, since I don't want to change the equilibrium equations that we have, we actually pre-multiply that T transpose matrix with the T matrix. transformation matrix, a global transformation matrix. And we know that these are orthogonal, so the product of these two matrices would be identity, which means that K times identity times degrees of freedom would be simply equal to K times degrees of freedom is equal to F, meaning that I have not changed the system of equations for equilibrium. So just by adding this T times T transpose in between K and D, or multiplying that between K and D, I can transform this T transpose multiplied with D. I can take these two quantities. So let me mark that as a parenthesis here. This quantity, this becomes a new D double prime displacement vector. This outside, so if I take all of these things and put them in one bracket, take these things and put them in one other bracket, and on the right hand side I'll have to pre-multiply by T transpose times FG. So that's how we get this equation. Okay. Let me ask you this. What property of matrices am I using by kind of reordering the multiplication of these matrices? Is it true that, okay, let me step back here. If I have two matrices, A and B, and I ask you to multiply A times B, let's say both are same size, n cross n, the product would be also n cross n, correct? A times B, if it is n cross n, the product would be n cross n. Would A times B, is that equal to B times A? No, it's not commutative. Matrix multiplication is not commutative, right, in general. How about if I have three matrices, A, B, and C, and to calculate the product, if I do AB first and then take that multiply with C, or if I take multiply BC first and then multiply with A, what property is that called? Associativity, right? So associativity means you can multiply any two matrices first as long as you keep the order the same. And here what we are doing is we are making use of that associativity property, that no matter how many matrices I have T transpose, KG, T, again T transpose and D. I have a long list of matrix and vector multiplication. It does not matter in what order I choose to multiply them, the result would still be the same. And the reason for pre-multiplying by T transpose, can anybody think of a reason for why we pre-multiplied with T transpose? Last time I kind of didn't mention it, but why would we? So all that we needed was really to have T transpose times DG, right? That converts this global displacements to that inclined displacements in 3 and 4. Why did I pre-multiply by T transpose here and express it in this manner, T transpose times KG times T? Any guesses or any thoughts on why we did that? Let me give you a hint. If you look at any one of the, let's say this example. In this example, if you look at this K global matrix, do you see any peculiarity about this K global matrix? Something that stands out? Any pattern in this? Right. That's right. Go ahead, Yicheng. That's
Symmetrical?
That's right. Stiffness matrices are symmetric. And not only symmetric, they are actually something called positive definite, which means really that that the stiffness of a structure is positive. It's just that statement. If I can't have a negative stiffness of a spring, I cannot have a negative stiffness of a structure as well. Otherwise, it will be unstable. So since this thing is symmetric, when you want to go and actually solve this system of equations on a computer, something like this, it is much more easy to solve symmetric system of equations. And there are lots of different types of solvers in any computer program you use. If you have a symmetric matrix, it's much easier to solve. So back to that question, when I pre-multiply by T transpose this entire equation, then what I've done is created a matrix T transpose times KG times T. Now KG, as we just saw, was symmetric. If I post multiply with TG, it becomes non-symmetric. So if I pre-multiply with T transpose, then any matrix that results from a symmetric matrix with T transpose before and T afterwards is also a symmetric matrix. So just to make the system of equations symmetric, we pre-multiplied that entire thing by T transpose. Okay. And then I'm calling this guy as a kg double prime, and I think on your handout I might have it as a single prime. So just to be consistent with this notation, let's call it kg double prime, because single prime is something that we've been using for individual element coordinate system, right? Here we are talking about inclined external roller coordinate system. That's for that I'll use a double prime. So kg double prime times d double prime times f, and I pointed out to you that this d double prime looks like this. 1 and 2 and 5 and 6 degrees of freedom remain unchanged. We have not transformed those. The only ones that we have transformed are the 3 and 4 at the location of the inclined roller. Okay, and this also helps us because now we can easily see that 3 prime is a free degree of 3 double prime is a free degree of freedom. 4 double prime is a fixed degree of freedom. So if I have my degrees of freedom in this way, I can clearly check which degrees of freedom are free and which degrees of freedom are specified. There's no degree of freedom that has a mix of fixed and free and specified. So once we have that, we can solve it exactly in the same way that we did the previous system. You divide it up into free and specified degrees of freedom, and you first solve the first row for the free degrees of freedom, then you solve the second row for the specified reactions at the points of supports. Make sense? So that's what needs to be done for your problem 3. And actually also this last sentence is also not on your handout, so I'll read it out here. After you have computed the dg double prime from this system and the fg double prime from this system, after you've done that, those two things have this weird structure. Some of the degrees of freedom are inclined, some are global, straight, and so on. So what we should typically do is to convert those back to the global system. And the way to do that, anybody can anybody tell me what should I do to convert dg double prime to global dg? Any thoughts, Joey? How did we convert this d to this d double prime? Let me ask you that, Joey, first. How did we convert this d to this double prime, d double prime? By pre-multiplying with T transpose, correct? So how do I convert D double prime back to D global transpose? Right, so this was T transpose. If I pre-multiply it with T, the global T matrix, that would convert it back to the global coordinate system, and the same exact expression for the forces. So we'll have Fg is equal to Fg double prime. And we convert them back to the global coordinate system just so that the rest of the Matlab code that I'll show you right now will be able to plot things correctly. Okay. So that also reminds me, I want to show you the sample Matlab code that I've already posted for the inclined supports. And let me make sure I open the right folder. So this 2D code, I've posted a separate Matlab code for those of you who've noticed. One of the Matlab codes is called Truss 2D _ basic.m. That's the main file for the stiffness method for trusses, and which hopefully you have been using to solve problems 1 and 2 for your homework 8. Right? That's the main file. For inclined supports, I said that you would have to modify this main file, and I've already given you a modified Truss 2D with incline.m as a template for what modifications are needed. So let me run you through those modifications. Uh, but before I go there, let me also point out exactly what is needed. What we did in this was took our original system of equations and we did exactly this modification. Pre-multiply with T global transpose, post-multiply with T. That's all we need to do, okay? So first of all, we need to construct this T global transpose. We need to construct the double primed system. And after we solve it, we need to convert it back. That's what we need to do. So looking at that code, hopefully, if you saw, there is this empty line on line 37, which you need to fill in. What that line does is it creates a global, it needs to create the T global uh, transformation matrix. So what I've done here is I've initiated the T global to be equal to I 2 times number of nodes. Anybody know what this command I does? In Matlab, go ahead. Makes an identity matrix of the size of 2 times the number of nodes. Why 2 times the number of nodes? That's the 2D problem, and each node has 1 degree of each node has 2 degrees of freedom. So the total size of my global system is always 2 times number of nodes for 2D problems. So what this command does is makes an identity matrix, just like I showed you in the last lecture. First thing I did was make this matrix and wrote 1 all across, right? That's the 2n cross 2n identity matrix. But then I need to go into the right location and change by cosine, sine, minus sine, cosine. That change is exactly what I'm asking you to write here. So you need to pick out the correct degrees of freedom in TG and modify those to basically Tmat degrees of freedom, cosine, sine, cosine, minus sine, sine, and cosine. If you put that in the right location in that big T global matrix, it'll be the correct global transformation matrix. Once you have that correct global transformation matrix, I'm asking you to calculate the transformed stiffness matrix, the transformed force vector, and the transformed displacement vector. What should those be? Those should be exactly what I have here in my notes. Those should be these guys. Okay, so it's not too complicated there either. And then finally, you solve. This system would be very well, this statement or these lines would be very similar to what is already there, but you would of course need to solve this system, not the original global system. And then after you solve it, you convert it back to the original global system. That's all that it needs, okay? So I'll let you figure this out. And of course, if you have questions, you can post them on the discussion forum or bring us to our office hours. Let me show you the example that's there in the notes for this. So the example is exactly this problem. And I'll take, I'll go back to my set of codes. I do have a similar filled out code that I won't show to you, but I'll use this code to run this problem, and this problem is, I believe this problem is 4. So let's input 4, choose input 4, open, and I think it'll already run and complete. So let's just first check the results, what it looks like, and then I'll show you how it computed those results. Note that this bottom corner was indeed a roller support. It should be free to move along this direction. And indeed, it moves exactly in that direction, not perpendicular to it. In the perpendicular direction, I have the reaction here, okay? If you use the 2D basic code that I gave you to run a similar inclined support problem, depending upon what input file you have, it may or may not work. But if it works, it will not give you the correct solution, something like this, okay? You do need to make those changes and use a different main file, the 2D, Truss 2D with incline.m. You need to correctly fill it out and then use that file to solve problem 3. So let's very quickly run through the steps of this of how this problem was solved. Let me open back the editor. Um, um, what do I want to show? Right. Um, Open selection. So I'll show you one stiffness matrix, that's the global stiffness matrix transformed, and this is the original stiffness matrix. I think I want to also write out some numbers here. Um, so this was the global stiffness matrix, and as it's mentioned in the handout, I'm not going through those same steps as I went through last time, showing you how each one of these matrices is constructed. I hope you understand that now that in this truss there are three elements. So if you remember when we went through that loop over elements, it will go to the first element and first it will compute what? For each element, you remember what we did first? We computed the local, the element stiffness matrix in the local coordinate system, right? That's the first thing we computed. For this particular element one, would that, yeah, it would be the same as the global coordinate system because it is oriented in the horizontal direction. For element two, which is in the vertical direction, it will not be the same, but it will be very similar. You look at this K2, this has non-zero entries in 2, 4 rows and columns. With this is the element stiffness matrix for element 2 in the global coordinate system. In the local coordinate system, it would have been exactly this matrix up in 1, 3, 1, 3 rows and columns. Okay, so transformation for horizontal and vertical members is either trivial, like for element 1, or very simple for element 2. Transformation for inclined members takes some amount of work. Um, so for element 3 here, it is inclined. You calculate the local coordinate stiffness matrix, convert that using the transformation matrices to the global coordinate system, and we get 1, 2, and 3. These are the element stiffness matrices for this truss. What do we do after we compute element stiffness matrices? After computing, say, the first element stiffness matrix, what did we do in the Matlab code? Anybody remember? We assembled it into the bigger global stiffness matrix, right? We started out with a big matrix of zeros, and what would the size of that be for this particular problem? 6 cross 6, there are 3 nodes. 6 cross 6, we started out with 6 cross 6 zeros. And now let's make sure that I can, using different colors, I'll use blue for element 1. So I have this 4 cross 4 global stiffness matrix for element 1. With green, I'll mark element stiffness matrix for element 2. Again, a 4 cross 4. And with purple, I'll mark element stiffness matrix for 3, which is again a 4 cross 4. And let's see whether this global stiffness matrix that I have on the next line makes sense. Where should this K1 go into the global system? Right, it should be connected to nodes 2 and 3. So that's degrees of freedom 3, 4, global 3, 4, and 5, 6. Later on, we'll modify this 3, 4 to 3 double prime, 4 double prime, but not yet. Right now, we'll just use 3 and 4. So let's see. That's 3 to 6. Let's mark that up here in blue. That would be this guy. Is that right? Yep. So hope you are able to kind of discern that these 4x4 numbers are already in here. Okay. Then we have K2, which is connected to nodes 1 and 2. So those would be contributing to degrees of freedom 1, 2, 3, 4, right? And that is in green. So I'll mark that in green up here. So that's stiffness matrix from the second element. That's components from the first element. And finally, we have elements from element 3, which is connected to nodes 1 and 3. So that would be degrees of freedom 1, 2, and 5, 6. So this particular purple matrix would actually get split into two different locations, just like the hand exercise we did maybe a couple lectures ago. It would go to 1, 2, and 5, 6. So let's do that. For purple, it would go to 1, 2 here, 1, 2, and 5, 6 here, 1, 2, and 5, 6 here, and finally 1, 2, and 5, 6 here. Right? So this is exactly like what we did, the hand exercise that we did. But this way, we have assembled all the element stiffness matrices into the global stiffness matrix. So this global stiffness matrix is in the global coordinates, right, written in blue. Since we have this 3 and 4 in the inclined position, I need to construct a transformation matrix which looks like a 6x6 identity matrix, but the 3x3 or the 3 and 4 components will have cosine, minus sign, sine, and cosine. And the angle is 45 degrees. So anybody know what this number should be in terms of fractions? 1 over square root 2, which is 0.707, right? So that's cosine of 45 or sine of 45. So that's what this transformation matrix is. And to construct the transformed, or again, I should write it as a double prime, not a single prime. So this is a double prime. Kg double prime is nothing but T transpose times K global times T. I get a big modified matrix of which the only things that have changed are, the only things that have changed are the 3 and 4 rows and columns. You should be able to verify. Actually, no, the only things that would change would be not just that square, but the entire 3 and 4 rows and the entire 3 and 4 columns. The numbers outside there should not get affected, right? These numbers should not get affected, but everything here has changed. So I'll mark that maybe as partial hatched, just to tell you that this is the effect of that transformation matrix, that these numbers got changed. Now using this, I can calculate the transformed displacement vector and the transformed force vector, convert it back to the global transformation vector. That's there. This u, as we just said, was equal to u transformed, and this f is equal to again transformation times f double prime. So in the Matlab code that I showed you, what you need to do is to construct this kg double prime and construct, by the way, this guy f, what I'm calling f1 is really f double prime, and u1 is u double prime. Okay, so you need to construct kg double prime, u double prime, and f double prime in the Matlab sample code that I gave you. Okay, that should allow you to solve problem 3. Any questions before I move on to the effect of, go ahead, Miles.
The K1, K2, and K3 matrices, those are still global.
These are global coordinate systems, yes. Yeah. Because before assembling them, we do need to convert them to global coordinate system, right? In the local coordinate system, all these three matrices would look, at least in pattern, they would look like this. The numbers would be different, but in pattern, this and this would look like this because one is horizontal, the local is the same as the global, right? Question, Nate?
Is the TG matrix being hard-coded in with those sine cosine values?
No, it's not, because that's what you need to create back up on this line. So depending upon the angle of the inclined support and the location of the inclined support, this part of the code actually finds out which degree of freedom it is, and then finds the angle based on, first of all, converting degrees to radians, pi over 180, and then calculates the cosine and minus sine and sine and cosine. It calculates that sub 2 cross 2 matrix for you. So, okay, so this TMAT TMAT DOFs that I'm calling, this is the same matrix, exactly the same matrix as this small 2 cross 2. Your job is to take this 2 cross 2 and put it in the right location in the uh, global system, transformation matrix. Go ahead, Nate.
So as far as the input file goes, that third column that said displacement is now the angle?
You mean input file? Let me open
It
up.
has to be able to find the angle.
Right. So, for example, the Truss 2D4.txt that I also posted on Blackboard, it says that boundary conditions, there is node 2, which has degree of freedom 0 is what I'm using to say that it's an inclined support. And the angle is 45 degrees measured from the positive x-axis. So what this says is that the angle at that point is 45 degrees to the positive x-axis. That's all that is saying. So the code that I've given you will read it correctly. So in terms of input file, you should be able to write something extremely similar to this for the problem that I gave you. Okay. The only changes that you would need are needed in this Truss 2D incline. First of all, make the T global matrix and then use it for the transformations and the inverse transformations. That's all that's needed. Okay. All right. Let's move on. You had another question, Nikhil?
No, it was the
Same question. Okay. Let's move on to this problem for effect of temperature and fabrication errors. So you remember back when we were talking about the virtual work method, we said that we can treat these effects as small initial changes of length. Okay, and again, I think I want to emphasize this point. When we were doing the virtual work method, where is that? Sorry, it's been a while, so we need to find it out. Yeah, there we go. When we were talking about the virtual work method, this is a common mistake that I've seen. Just by changing L in NL over AE will not do anything, will likely be extremely small effect. That is not what the virtual work method does to account for small changes in length because of misfit or temperature change. If there is a misfit, the actual displacement is what we are calling delta L, right? If there are fabrication errors in one or more elements, then you need to take D, the actual displacement, which gets added to the displacement from any load. So NL over AE plus delta L is what you need to use. Similarly, if there's a temperature effect, you need to add that to the displacement due to the loads and then calculate the internal work in that big table, right? Just changing this L will not do much, and actually is technically not correct. So let's go back to this stiffness method. That's the exact same logic that we'll use here as well. We're saying that for a particular element M, if there is an initial error due to either temperature change or due to fabrication errors, that length, we assume that that the change in length is delta L. If delta L is positive, the member is too long. If delta L is negative, the member is too short, right? So what we are saying is that we'll account for this by actually accounting for the force that it creates in the truss. So what we'll do is we'll think of our original truss. So we think of our original truss, and if all the members were the correct length, then we would have a nice geometrical truss, right? Since one of the members is too long, okay, since one of the members is too long, what I'll do is I'll initially apply a force to make it too short exactly by that amount, delta L, just so that I can get it to the correct length. So I'll apply forces to it, what I'm calling Q0 forces. Only to this member, I'll apply Q0 forces to shorten it to the right, to the correct length, right? Once I've done that, then I can put it back into the truss as if it was unloaded, and then apply any other external loads on top of it and solve the system. So let's see how this works. We're the initial uh, the initial force that I need to apply to convert it, or to correct the delta L change in length, what should that be? How can I find that? If I say that a member is too long by delta L, what amount of force do I need to apply to it to get it back to the correct length L? What would that be? So, okay, here's the question. If I apply a force P, what is the change in length of a truss member? PL over AE. Now I'm saying, let's write that as a separate page here. So delta for a given load P is PL over AE. I'm asking you the reverse question that if I know delta, how do I find P? AE over L times delta, so I'll call this delta L, okay. If I know the load P, then I can calculate delta L as PL over AE. If I know delta L, I can calculate the load needed to affect that delta L as PL over A or AE over L times delta L, right? So that's the force. That's the force that would be needed to create a change in length of delta L. So that's exactly what we'll do with this stiffness method. This force would be oriented along the x prime direction. So in the local coordinate system, which I'm writing in purple here, that would be equal to AE over L times the delta L change in length, and minus 1, 0, 1, and 0. Does that make sense? The force on the member is in this direction. The force on the node would be in the opposite direction. That's why I have a minus 1 here. This is minus x double prime direction. This one is the positive x prime direction at node J. This is hopefully you recognize this from when we were doing local stiffness matrix. So next step, all we'll do is we'll take this local initial forces and convert them to global initial forces. And to do that, let's quickly check. To go from local to global, I need the transformation matrix, not the T transpose. I need transformation matrix itself. So I'll take T 0, 0, T. That's a transformation matrix, and I'll take my Q double prime at I and Q0 double prime, sorry, not double prime, single prime. This is the local system, not the inclined system. And Q naught J. So first compute the forces on the nodes in the local coordinate system, convert them to the global coordinate system using transformation matrix, And then this transformation matrix can be simply, well, I think the next line as I have it in my notes is not too complicated. It's just AE over L times delta L, same transformation matrix, and minus 1, 0, 1, 0. So the idea is that we'll apply these global forces in addition to whatever forces are given for the problem. Okay. So these forces would be acting on a particular element, and we are adding them to whatever forces are already there. So, which is basically what this is. You remember, this was the system that we originally came up with, as if there was no delta L change in length, either due to temperature or due to misfit or anything. This was the system that we originally got. What we're doing is we are taking this initial forces just to make that member fit back to the correct length. And we can do that by applying these additional forces to the global system. Okay, so that's the idea. In addition to any forces that are already applied to the truss, we apply these forces to that particular member. And once we have that, we can solve it. We know how to solve this system. On the right hand side, we have a new 2 cross 1 vector. This is a plus sign. So the result of that is a new 2 cross 1 vector. We know how to solve that. After you've solved it, you can go back and calculate the internal forces in the members. Now that calculation also does require a little bit of care here. Since we added this force as an external force to our truss, we need to subtract it back out from the member forces. Okay, we need to subtract it back out from the member forces. So that's why you calculate the element force using this element force displacement relationship and subtract that out. And let me show you this through an example. I think that will make more sense. So here we have this same truss, which is an indeterminate truss, as we pointed out last time, indeterminate to degree 1. Member 2, this guy, is too short by 0.01 meters, 1 centimeter. Determine the force in member 2, and AE and all those things are given. So to solve this problem, there are no other external loads. There are no support settlement or anything like we had in the previous case. So since this member 2 is too short, let me ask you this. Do you expect, what kind of forces, tension or compression, would you expect in member 2 in the final deformed configuration? It's too short. Yeah, so the rest of the members of the truss would try to pull it apart. So it would be in tension. And that would cause what type of forces in members 1 and 3? Compression. Right? So since member 2 is too short, it's going to try to pull that node 2 down, and that will cause compression in the vertical and horizontal legs. Make sense? So that's what we should expect as a result. Now, to get to that result, what we are doing is, since this guy is too short, I need to apply initial forces to the truss to extend it back to its correct position, right? Those initial forces is what I'm calling QL0, which is equal to AE over L, 8E6. So just to, in case you haven't noticed, in Matlab, 8E6 is how we represent 8 times 10 to the power 6 in Matlab, times delta L. So this is AE times delta L divided by 5, which is the length of this member. So this guy out here is, this entire thing is AE over L times delta L, and this matrix is equal to minus 1, 0, 1, 0. Right? This is exactly what we had on the handout on the previous page. So this is the Q local forces that I need to apply along the member to extend it back to the correct location, to the correct length. I will take the transformation matrix for this element 2. This is the transformation matrix for element 2. Clearly, you should be able to see the structure: cosine, minus sine, sine and cosine, cosine, sine, and minus those 2 cross 2 in those locations. And to convert the initial forces from the local coordinate system to the global coordinate system, I just pre-multiply by this transformation matrix, which gives me QL0. These are the forces that I need to apply to nodes 3 and 2. Okay, so let me mark that here. What this means is that I'll be applying 12, 8, I'll be applying 12, 8, 0, 0, and actually it will be the other way, sorry. It will be this way: 12, 800, 9, 6, 0, 0, and same thing here: 12, 800, and 9, 6, 0, 0. Those would be the forces that I would apply to this truss to solve this problem, just so that I can account for that small delta L change. And these forces you would have to specify as part of an input file. So if we go to that last example that I had, I think it was 5, Truss 2D basic. And for this problem 4, your Truss 2D basic is what you would use. So I'll open up file 5, and I hope that's the right one. Yep. And you can see that this member got shortened by a little bit. The force in here is negative, meaning compression. These guys, sorry, the force here is negative, which needs to be corrected by the amount that's given in this handout. So you solve the global system exactly in the same way, calculate displacements and forces. This number 67407, this is the internal force that the Matlab code will plot for you. That's 67407, that's the internal force. But since there was an initial misfit, Matlab does not know whether that force came from a misfit or from an external load. So you will have to manually correct for it, which means that you take whatever force you got from Matlab and you correct it by this amount QL0, and the correct amount of force in that member is 92593 tension, and the other two members do show the correct force. Okay, so very quickly, just to recap the idea here, if you have a member that is too short or too long by delta L, you calculate the local forces, convert those local element forces to global forces. These global forces need to be applied to this truss as part of an input file. And I think I'll show you that input file. That would be the last thing I'll show you, and then we're done. So this input file for that truss is exactly what we had as before: 4 nodes, 3 elements, boundary conditions at 3 nodes, and the nodal loads. So node 3 has loads 12, 800, 9600, minus 128, and 960. These are exactly the forces that I drew here. Okay, so you just have to make a new input file for problems that have a misfit, and then use the 2D basic code that I've given you to be able to solve that, and finally change the internal force in the member that was too short or too long. Okay. All right, so let's stop here, and then if you have additional questions, post them on the forum or bring them to my office hours. And this homework 8 part 1 would be due Monday. Okay.
question really quick.
Sure.